Hey students, Assalamu alaikum. Hoping you all will be fine. Today we will discuss about the amino acids and about their acid and base properties, about their reactions, how they react with the acids and the bases. The charge properties of the amino acids are very important in determining the reactivity of the certain amino acids, having different side chains and in the properties they confer on the on the proteins. So this is very important to know about the acid-base reactions or the reactivity of an amino acid. The reactivity of amino acid will determine what kind of properties it's imparting in the features of the proteins. Okay. Um, Amino acids, as far as their ionization is concerned, mostly alpha carboxyl and the alpha amino groups of all the amino acids containing their with their ionizable R groups, groups of uh, which is present in almost 7 amino acids. Most of the amino acids, their alpha amino group and their alpha carboxylic group, they function as weak acids and the weak bases in the aqueous solution. The pK of these functional groups depend on the chemical properties of the groups themselves, and it ranges between 1.8 to 2.4, and for the carboxylic group and for the alpha amino group, it's in between 8.8 to the 11. So this is the range range of the pK values. Sometimes amino acids make a dipole having the net charge which is equal to the zero, and such kind of dipolar amino acid is known as the zwitterine. Substances having this dual nature are amphoteric and are often called ampholites. Ionization behavior of the alpha carboxyl and the alpha amino group of the simple amino acids such as the alanine um, are like this reaction. Say for example, this is an amino acid. Look on this equation. Say for example, this is an amino acid. This amino acid contains net positive charge, which say for example, it's equal to the 1. When it removes the hydrogen from the carboxyl group, this hydrogen is when removed, this proton is when removed. So this carboxyl group will contain the negative charge on this on this molecule. So there will be a negative charge in the molecule. Now, carboxyl group is containing the negative charge. Amide group is already containing a positive charge. So this is negative and this is positive. They will cancel out the effect of each other. So the net charge on the molecule will become equal to the zero. This type of the ions, which are having the negative and the positive charge in the same molecule, and their net charge is equal to zero, such kind of ions are called the zwitterions. After losing a one hydrogen from the amide group, the amino acid will have a negative charge on it. So there will be a minus one negative charge because of this one. When one proton is released from the amine group. For example, if you can look on this diagram, this is the non-ionic form of the amino acid, and when it will make the zwitterine, there will be positive charge and there will be the negative charge. When zwitterine release one electron, one proton, carboxyl group, negative charge containing carboxyl group will impart the charge, and it will be, you can say, it will be net negative charge on this molecule, or 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 if there is zwitterine and this carboxyl group attain one proton from the environment, etc., wherever. So after getting this proton, net positive charge will be on the amino acid. Before looking on the titration curve, or before looking towards the distribution of charges on the amino acids or the acid-base properties of the amino acid, we must know a little bit, or we must recall a little bit about the Henderson-Hazelbalch equation. This is very important to remember this equation. The equation we have already discussed in our earlier lectures. Say for example, uh, when we proceed from the equation, say for example, I told you that there is so there is an example. So for example, this is H E when it is broken down into uh, H plus A, the chemical base. So when this is negative, this is will be positive. The pK will be the pKa will be the pK will be the concentration of H plus the concentration of A plus, I'm sorry, plus, no, not the plus, multiplied by the concentration of the conjugate acid base divided by acid. This is pK. Okay. So from this derivation, we got the express. So from the derivation of this equation, we got the expression pH is equal to pKa plus log A over HA. We found that we explained that this is actually the relationship between the pH and the pKa. This is actually the relationship. This was actually the equation of the Ka. So sorry, I'm making it clear for all of you. First, I thought to go through only, but I'm easy with this. Okay. So this is the Ka, and these are the values of the Ka. By multiplying both sides with the minus log, when we multiply both sides with the minus log, the values will be the log minus Ka equal to minus log. We split these two values. We split these values minus log H positive ion concentration plus minus log A negative concentration over HA over HA. This value is equal to the pKa. This value is equal to the pH. So pKa becomes equal to the pH plus, and this plus after multiplying with the minus, it will become the minus just a minute. It will become minus log A negative over HA or over the acid. So this is the equation. When we replace the values, when we change the position of the pH, we will get this expression. So this is the position. This is the position where A negative. Uh, this is actually the position where A negative, uh, and the concentration of acid is important in the equation. Okay, when we say that both of these values are in equimolar concentration, it means this equation must be, say for example, pH equal to, for example, pKa plus log of, say for example, plus log of 13 divided by 13. This 13 will be cancelled out with this 13 because both the substances are in, you can say the proton donor and the proton acceptors are in the equimolar concentration. So this will equal to log 1, and log 1 is equal to 0. When this value is equal to 0, this type of expression will be obtained. It means at this position when both the substances are in equimolar concentration, both the substances are in equimolar concentration, at that position pH must be equal to pKa. Now we are moving toward the titration of the simple amino acid. First of all, before looking into the titration, we must know about about the drawings and about the experiment of we must know about the experiment, that how this experiment could be performed. First of all, we make the solution of amino acid. First of all, we make the solution. Say for example, we make 0.1 molar solution of any amino acid. Say for example, we are dealing with the glycine. We are dealing with the glycine, so we make 0.1 molar glycine solution. Okay. Check. We will check its pH. Okay. After checking the pH, so for example, whatever the pH is, we divide this solution into the we divide this solution into two flasks. So for example, these are the two flasks. Equally divided into the two flasks. Here we will draw the columns. Volume, acid, say for example, acid or base, whatever. Here is the pH when treating with the acid. Here is the pH when treating with the base. Say for example, when there is no addition of any acid at the base. Okay, here this is the by unit, say for example. In here we will add 0.01 molar solution of HCl. We'll add 0.01 molar solution of NaOH. Upon each addition of the volume, we will note the pH. So for example, first we treat with the acid. So for example, we add 0.5 microliters, say for example. When the volume was 0, say for example, the pH was 5.7. We add 0.5 microliter. The pH is So when we add the acid, pH must be dropped down. Say for example, it's 4.3. And when we add the base, it must in this. Say for example, we are adding acid. In this class, we are adding the base. And when we add the base, the pH must raise. So we will continue the addition of solution until it reaches the pH up to the 2 or lower than 2, and we will continue the addition of base up to the pH reaches at the 12 or greater than 12. Now we need to proceed for the for making the graph. For making the graph, this is very important. On the graph paper, uh, we will draw a line on the x-axis, and in the center of this line, we will draw the y-axis. This is y-axis. Just a second. Okay. Center of just a minute. Okay. I'm sorry. I couldn't make the straight line actually. Just a minute. Just a minute. So remember this one and this one. Okay. So these are our x-axis and this is our y-axis. So then this is the addition of volume 0. This is here. This is 1. This is 2. So then this is actually 3. Oh, so on, whatever. And here 1, 2, 3, whatever. 3, 2, 1. Okay. Now, when the volume at 0, the pH was 5.7. By adding the acid, this pH will be dropped down like this one. Or if again I'm drawing, it will drop down like say for example like this one. And it will raise like this one. Or a little bit slow will make. Now we got these two lines. We got such kind of graph now. Okay. To make it more clear, so this type of graph will be made. After making the graph, we will divide the overall volume used by 2. We will divide the volume by 2 on both sides. Volume by 2. Okay. So for example, after dividing, we are getting the value here. And we are getting, so for example, value here. Okay. Now, these are the 2 points that we are getting. After getting these values, draw the perpendicular on the y-axis, or the perpendicular on the y-axis. The pH over here is equal to the pH over here. This is equal to pKa. Okay. Now moving towards our topic. This is all about how we do the titration and how we get the point of inflection, point of inflection on the curve or on the curve of uh, titration. Starting from the titration curve of the amino acid, look on this graph. On this graph, you can see that, say for example, we are getting 3 points on this graph. One point is PK1, second point is PK2, and third point is PI. The third point is PI. Okay. First, we divide the overall volume by 2, and by after dividing it by 2, we are getting the point here. So this is so the pH over the year. So the pH over the year is equal to the pK1, and the pH over the year is equal to the pK2. Okay, what are these pH? When we treat the amino acid with the acid at the lowest pH, the glycine is fully protonated. It is having the overall positive charge on this molecule, on this residue, this glycine. Okay. With the increase in the pH, it start losing protons. We can say the proton of the carboxyl group is being lost by the increase in the pH. Okay. At the pH 2.34, this is the position where you can say proton donor, where the proton donor and proton acceptor are equal. This is the position where the proton donor and the proton acceptors are equal. So I told you that at this pH, at the lowest pH, the glycine is fully protonated, and at this pH, where the pH is being equal to the pKa, protons donor are equal to the proton acceptors. Okay, just make it clear to be viewed easily. Second point of inflection is being obtained at the pKa2, which is 9.7 here. 9.7, if you can look here, 9.7. This is the first point, and this is the second. At the 9.6, at the 9.7 or 9.6, whatever. Again, this is the position where proton donors are being equal to the proton acceptor, and this is the position when NH3 is losing its proton. NH3 is losing its proton. NH3 is positive, and now it's losing its proton. After losing the proton, it will become NH2. Okay. Now, the third point, from where we are getting the third point. Third point is the point between 9.60 and 2.34. So, for example, this is PI. PI is actually equal to PK1 plus PK2 divided by 2. So this value is 9.6 plus 2.34, dividing it by 2, we are getting the second point. Now we are getting third point, which is 9.57. What is this 9.7? What is this? This is actually the isoelectric point. Now, from this graph? What kind of information we are getting? What kind of information we are getting from this graph? This graph tells us that at the near the pH 2.34, near the pH 2.34, there is a region which is resisting against the pH. And again, between the 9.60, there is a position which is resisting against the increase in the pH. So the first point that we are getting is at these two pHs, these two pHs, we can make the efficient buffer because buffer need to resist the pH. So at these positions, we can make an efficient buffer. Second position. The PI is telling that this is actually the point where zwitterions are existing, where there is no net charge on the molecule, on the residue, on the amino acid, on the glycine. There is no net charge on the glycine. Okay. Moving down toward the PI, moving down toward the PI, most of the residues are being protonated. Most of the residues are being protonated. And by moving upward, or we can say moving downward from the PI, isoelectric point, or zwitterion, the amino acid is positively charged, and by moving upward of the isoelectric point, the amino acid is negatively charged. So from this graph, we can check out, we can find out the distribution of charges. We can find out the distribution of the charges on on different pHs. The next titration curves is for the glutamate. There are some amino acid residues, around 7 amino acid residues, which are having the which are having the ionizable alkyl group. Now, looking on the glutamate, if you look on the glutamate, glutamate is containing the ionizable glutamate is containing the containing another you can say another carboxyl group. Because of this carboxyl group, the net charge on the glutamate is negative. Okay. When all the groups are are charged, or the molecule is, for example, the molecule is fully charged, or you can say when we treat it with the acid at the lowest pH, there is a net positive charge on the molecule. There is net positive charge on the molecule. Okay. After releasing one proton, the overall charge on the glutamate will be 0, because here is the positive one. It will release one proton, and there is a by the release of one proton, the net positive charge, the net charge will be equal to 0. Okay. After releasing the second proton, after releasing the second proton, the net charge on the glutamate will be -1. And when the proton from the amine group will be released, and the proton from the amine group will be released, there will be a net negative charge, which is -2. Look on this. Now, we need to find out, okay, this is the titration curve of the amino acid glutamate. pK1 is obtaining, we obtained the pK1 at 2.19. We are obtaining pK2 at 9.67. So the formula for PI is pKa1 plus pKa2 divided by 2. This was okay, but now there is the problem. There is another pK value, which is pKr,
Now, what will be the formula for the pi? Either on the second position, either the formula will be pk1 plus pkr or pk2 plus pk2 plus pkr or pk1 plus pk2 divided by 2. What will be the formula? Now we need to check where the Zwitter answer being formed. Where the Zwitter answer being formed. If you look after the pk1, which is equal to around say for example 3 point something 3.90 is equal to whatever. After the pk31, okay, after this one, Zwitter ions are being formed. Zwitter ions are making. Because there is a net positive charge after releasing the one proton, after releasing just release of one proton, the net charge in the molecule will be net charge in the amino acid will be zero. Okay. The net charge will be zero. After releasing this proton, this proton, the net charge will be -1, and after releasing this proton, the net charge will be no. No, the problem is no. If you look on net charge, the deuterion are being formed between the pk1 between the pk1 and between the pk1 and after the release of ionizable alkyl group. Again, I'm saying that first, say for example, this proton is being released. Secondly, from the second carboxyl group, the proton will be released. This say for example this pka is say for example this pka is say for example this pha this pka is uh, for the carboxyl group of the amino acid, and this pka is for the carboxyl group of the alkyl group R chain. So the zwittered ions are being formed after the deprotonation of carboxyl group and the carboxyl group of the alkyl group. So the pK, so the pi must be equal to pk1 plus pkr pkr divided by 2. You can see we need to look where the net charge is being zero. The net charge is being zero after the pk1 and pkr. So pk1 is 2.99 and pkr is 4.25. Say for example 4.25. So the pi will be 2.19 plus 4.25 divided by 2, and it will be equal to 3.22. So the pi of the glutamate is 3.22. This is actually the titration curve regarding the aspartic acid. So that's why the values are different. That's why the values are different here. But don't worry about it. And then there are almost same procedure in both of these. Titration curve of the histidine. Similarly, when we treat this molecule with the acid here, after being the fully protonated, there is net positive charge which is +2, which is +2. Okay. Now look, after releasing the carboxyl group proton, the net charge will be +1. Second is here the positive charge. After releasing this alkyl group, after releasing the proton of the alkyl group, the net charge will be equal to 0. Now, this one, the net charge will be equal to 0, so there is the pKr, and the minus 1 will be obtained after the release of this one, this proton. So these are the two values. We need to choose the values where the center of the values are equal to 0. Okay. So plus 1, 0 and minus 1. We are choosing the value plus 1, 0 and minus 1. So these two are the pKrs. So in this case, pKa2 plus pKr divided by 2, and this will be equal to 7.5. Whatever. There is plus 2, there is plus 1. After release of proton, it will be equal to 0. Here the zeta ions are being formed, and here is minus 1. So 9.331 and 6.024 second divided by 2, the value will be equal to 7.69. This is procedure how we determine the pK values of the amino acid. These are the amino acid values. These are the pK values of the different amino acid. Here you can see there are some amino acids which are having the ionizable alkyl group. So the pK value for their alkyl group will be separate. This is all about the today's lecture. Tomorrow we will discuss about the asymmetry of the. Good luck. Allah Hafiz.